Hey everyone, and welcome to today's Explainer. I know you're all totally geared up for tomorrow's test, so we are going to make this an intense, highly focused study session on 12th grade chemistry, specifically Unit 7. Let's just dive right in because we've got some really crucial ground to cover. My absolute top priority today is to make sure you walk into that exam room tomorrow feeling bulletproof. Here's our game plan for today. We'll start with an intro to Section 7.3, move into rate law theory, tackle writing rate laws, get into concentration and orders, hit a quick chapter summary, and finally, we'll wrap up with some practice MCQs to really lock it in. All right, Section 1, Introduction to Section 7.3. We're looking at a full overview of your TOOT guide, page 61. Today, we are going to conquer the book back 2-mark questions exactly as they appear. We're hitting 2, PY1, 8 PY1A, 10, 12, and 18. Let's break this whole thing down. Moving on to Section 2, Rate Law and Constant Theory. Question 2 from the June 24 exam asks us to define rate law and rate constant. For the reaction XA plus YB arrow products, the rate law is rate equals K times A to the power of M times B to the power of N. Here, K equals the rate constant, and the order M plus N is the sum of the powers of concentration terms involved in the experimentally determined rate law. Definitely lock that formula in your mind for tomorrow. Okay, this next one is a massive previous year question, PY1, from the August 21 and June 23 exams. It asks for the differences between the rate and the rate constant of a reaction. Let's contrast them. While the rate of the reaction represents the speed at which the reactants are converted into products at any instant, the rate constant of the reaction is simply a proportionality constant. Secondly, the rate of the reaction is measured as a decrease in the concentration of the reactants or an increase in the concentration of products, whereas the rate constant of the reaction is equal to the rate of reaction when the concentration of each of the reactants is unity. Finally, the rate of the reaction depends on the initial concentration of reactants, but the rate constant of the reaction does not depend on the initial concentration of reactants. You really need to memorize these 3 distinctions exactly as they're written here. Section 3. Writing rate laws. This is where we get into practical application. The trick here is taking a word problem and turning it directly into a mathematical formula. Question 8 asks to write the rate law for the following reactions. Condition A is a reaction that is 3/2 order in X and 0 order in Y. The exact answer is rate equals K, X to the power of 3/2, Y to the power of 0. Condition B is a reaction that is second order in NO and first order in Br2. The exact answer is rate equals K, NO to the power of 2, Br2 to the power of 1. Honestly, it's really that straightforward. Let's look at another one. This brilliantly illustrates how examiners might test this. It's PY1A, marked for March 26. The prompt says, write the rate law for the following reaction in which the order with respect to the reactants X, Y, and Z are 1/2, 3/2, and 0 respectively. You can write this in 2 valid ways. Answer 1, rate equals K, X to the power of 1/2, Y to the power of 3/2, Z to the power of 0. Or, because anything to the power of 0 is 1, you can write the second answer. Rate equals K, X to the power of 1/2, Y to the power of 3/2. Both of these are perfectly acceptable. All right, Section 4, Concentration and Reaction Orders. This is the math-heavy portion, so stay laser-focused with me here. Let's tackle question 10. The prompt reads, the rate law for a reaction of A, B, and C has been found to be rate equals K, A squared, B, L to the power of 3/2. How would the rate of reaction change when rate equals K, A squared, B, L to the power of 3/2? We've got 4 sub-questions here. Number 1. Concentration of L is quadrupled. Let's plug that in. 4 to the power of 3/2 simplifies to 8, so L becomes 4L, giving us rate equals 8 times K, A squared, B, L to the power of 3/2. The final answer, rate is increased by 8 times. Number 2, concentration of both A and B are doubled. A becomes 2A, B becomes 2B. Simplifying gives us rate equals 8 times K, A squared, B, L to the power of 3/2. The final answer, rate is increased by 8 times. Number 3, concentration of A is halved. A becomes A over 2, 1/2 squared is 1/4. This gives rate equals 1/4 times K, A squared, B, L to the power of 3/2. The final answer, rate is reduced to 1/4 times. And number 4, concentration of A is reduced to 1/3 and concentration of L is quadrupled. We plug in A over 3 and 4L.
This mathematically becomes rate equals 8/9 times k a squared b L to the power of 3/2. The final answer, rate is reduced to 8/9 times. Guys, make sure you actually practice writing out every single one of those steps.
Next up is question 12. For a reaction x plus y plus z arrow products, the rate law is given by rate equals k times x to the power of 3/2 times y to the power of 1/2. What is the overall order of the reaction, and what is the order of the reaction with respect to z? First, to find the overall order, we just add the exponents. 3/2 plus 1/2 gives us 4/2, which equals 2. Second, since z does not appear in the rate law equation, the order of the reaction with respect to z equals 0. Moving right along, question 18 asks us to identify the order for the following reactions. For reaction 1, the rusting of iron, the answer is slow reaction, difficult to predict rate, order. Moving to reaction 2, the radioactive disintegration of carbon-14, the answer is first order reaction. Finally, reaction 3, 2a plus 3b arrow products. With rate ka to the power of 1/2 b squared, we simply sum the powers. Order equals 1/2 plus 2. To get a common denominator, that's 1 plus 4/2, which equals 5/2. Section 5, Chapter Summary. Take a breath, you made it through the line-by-line breakdown. Over the last 7 question slides, we covered the absolute core rules of Section 7.3. You now know the precise mathematical definition of a rate constant and a rate law. You've memorized the 3 distinct differences between reaction rate and the rate constant, especially the fact that the rate constant does absolutely not depend on initial reactant concentration, and you've seen firsthand how overall reaction orders are calculated simply by summing up those concentration powers. You've got the tools. Now it's time to test them out. Section 6, Practice MCQs. It is active recall time. All right, are you ready? I'll read the question, you guess the answer in your head, and then we'll reveal it. MCQ 1, based on the PY1 theory, which of the following defines the rate constant of a reaction? A, it depends on initial concentration. B, it is a proportionality constant. C, it represents speed at any instant. D, it is measured as a decrease in reactance. Think back to that comparison table we went over. Got your answer? The correct answer is B. It's a proportionality constant.
MCQ 2, based on question 8, what is the correct rate law if a reaction is second order in NO and first order in Br2? A, KNO shall Br2. B, KNO squared Br2 squared. C, KNO squared Br2 to the first. D, KNO to the first Br2 squared. Remember, you just take the words and turn them into exponents. Do you have it? The answer is C, KNO squared Br2 to the first. Awesome. MCQ 3, pulling from that math-heavy question 10, specifically part III. If rate equals Ka squared B L to the power of 3/2, what happens if the concentration of A is halved? A, increases by 8 times, B, reduced to 1/4 times, C, reduced to 8/9 times, D, remains same. Think about it. Since A is squared, 1/2 squared becomes 1/4. Lock in your guess, and the answer is B. The rate is reduced to 1/4 times. Okay, final question. MCQ 4, based on question 18.3. What is the overall order for a reaction with the rate law, rate equals K, A to the power of 1/2, B squared? A, 1, B, 3/2, C, 2, D, 5/2. Just add 1/2 and 2. Got your answer? The correct answer is D, 5/2. Look at that, you totally crushed it. My strongest advice tonight is to go through these exact concepts and practice writing the formulas from memory one last time. You've perfectly reviewed the TOOT Guide Worksheet 7.3. But I want to leave you with a thought as you close your books tonight. If you were working as a chemical engineer in a massive industrial plant, how would mastering these exact rate laws allow you to manipulate concentration variables to maximize your product yield safely and efficiently? Think about the real-world power of the math you just learned. You are fully prepared. Good luck on tomorrow's test, and I'll catch you in the next explainer.